Let's do an example of the slicing method. The slicing method can be used to find the volume of a solid. In this problem, we are looking at a frustum. A frustum is a cone where a portion of the cone has been removed. In this setup, we want to assume that we have a cone of radius r and height h. We cut that cone in half and remove the top half, resulting in this frustum. Let's make a copy. Height of this frustum is h over 2. The base of the frustum is a circle with radius r, and the top is a disk of radius r over 2. We want to find the volume. In order to obtain information on the frustum, we're going to extend the height of the frustum to the original height h, allowing us to draw a right triangle with a height measuring h and a base measuring r. The r corresponds with the radius of the base. As we've extended this height, we could note that this height, when we cut it in half, will correspond with the top of the frustum. And then I've indicated that I want the tip of the triangle to correspond with the 0 and the bottom of the triangle to correspond with h, meaning that as I measure from the top, I want an x value beginning at h over 2 and the x value to be taken as large as h. Okay, that's going to turn out to be our bounds of integration. Let's draw a second right triangle, a similar right triangle. Measuring from the top, come down to x. That's this height of the pink right triangle. And then at that height of x, measure horizontally out until you reach the hypotenuse. As that measurement will depend upon the depth in which you reach down, x, let's term that measurement r of x. This is the quantity that we want to determine. Let's set up similar triangles. We can look at the ratio of r over h, that's on the big triangle, and set it equal to r of x over x. Write that down. Nice. Once again, we want to find r of x. That's easy to solve for. Multiply both sides by x, and we have an expression for r of x. What are we going to use this for? Well, let's come back and look at a vertical cross-section of the frustum. And we've measured down into the frustum. And at this depth, we have the horizontal right line segment corresponding to the radius of a cross-section of the entire frustum. That cross-section is then going to have some area, a of x. As this is a disk, the circle of radius r encloses the disk and has area pi r squared. Plug in our r of x, r over h times x, get r squared over h squared on x squared, and multiply that by pi to come up with a of x. Beautiful. Now, bringing this all together, we have the previous picture. We have our area function that we know measuring from the tip of the cone that we should come down to at least h over 2 up to h, providing us our bounds of integration, h over 2 up to h. These are x quantities, and that each of those depths we want to determine the area of the disk taken to be the horizontal cross-section of the frustum. Nice. Plug in a of x. Here it is. And here it is appearing as the integrand. This integrand is very nice. It's a constant times x squared. And we know that x squared integrates up to x cubed over 3. And then when we evaluate at the bounds, we'll have h cubed minus the quantity of h over 2 cubed, which gives you h cubed over 8, 2 to the third. Taking the difference, 8 minus 1 gives us our 7, and in the denominator, 3 times 8 gives us a 24. And the h cubed cancels with h squared, leaving a single h in the numerator. Beautiful.